Thank you for downloading this podcast from Talk Radio 702 and 567 Cape Talk. For more podcasts and more information on your number one news and talk station, please visit 702.co.za or capetalk.co.za.
Your family, your community, your country, your responsibility. Be the best citizen you can be. Click on the Leader Say banner on this website to find out about your rights and responsibility.
The Naked Scientist on Talk Radio 702 and 567 Cape Talk with Rudy Clappy.
Chris, lovely to chat to you again. Welcome.
Hey, good morning.
Yeah. Okay, so we've got lots of questions coming from last week's conversation with Eusebius, and our lines are already open for you. Please join us. We are stripping science to its bare essentials. And on 02144600702. And no, that's the wrong number. 446, which one is the 446, Thomas? 0567. That's Cape Talk. I beg your pardon. 011-883-0702. What do you want to know? Are you curious about life, about science, about biology? This is your show. I have a question from the Lance Armstrong saga. Chris, somebody wants to know, please can you explain the science behind blood doping? How does it work?
Okay, so what an athlete needs to do in order to perform well is to make sure that their muscles have got enormous amounts of energy and oxygen. And the way in which energy and oxygen reach the muscles is via blood vessels. And when blood goes through the heart, it then goes through the lungs, and the red blood cells in the blood pick up oxygen from the lungs and then carry those to the muscles. So what you can do is to take some blood out of the body at some point, like a blood donation, and store that blood. This leaves your body with slightly fewer red blood cells, and so a signal comes from the kidney called erythropoietin and says, make up the lost blood volume. That's a normal protective mechanism that's there to keep your level of blood correct and also to replace red blood cells that are getting old and dying. So your body then makes new red blood cells, putting your level of blood and red blood cells back to what it should be. Mm-hmm. You then, just before your important race, reinfuse the blood that you took out previously and had stored, and now what you've got is a bigger circulating volume temporarily, but more importantly you've got a bigger hemoglobin. Your red blood cell count and the hemoglobin they contain is much higher than it should be, and this means that you per unit blood can store and transport more oxygen and carry away more carbon dioxide than you otherwise would be able to. And this makes your muscles perform better and more efficiently for the time that blood or extra blood moves around in the blood vessels. And so it gives an advantage chemically, biochemically and functionally to someone who does this.
Mm-hmm. Thank you very much. Let's go to Jenny in Durbanville. Hi there, Jenny.
Hi, Rudy. Hello, Chris. I just want to ask the question, where does the colour of the food that we eat, like a beetroot or something like that, go in your body?
Where does
because
the colour
it doesn't
go?
come out that colour.
Well, it's interesting that you mentioned beetroot because there is actually a condition called beeturia, Beeturia, and this is in a small proportion of individuals in the population. And when they eat beetroot or beetroot that contains similar chemicals, beetroot's red because it has something called anthocyanin in it, this does not get broken down in the body and it is absorbed in the intestine, it goes around in the bloodstream, and because it is water soluble, it is then filtered out by the kidneys. And this can produce some rather scary symptoms because people do sometimes do red wee. Occasionally they also can produce rather red-coloured number twos, and this scares the life out of people, but it's because they're not breaking down that pigment. So some food and plant pigments are not removed in the body, they're merely absorbed and then filtered out intact, where they can impart the same colour to what leaves the body. Many of them, though, are big molecules that are not very chemically stable, so when you put them into yourself, the acid in your stomach, the enzymes that are there, and the fairly nasty, harsh environment of your intestines, and the bacteria that are living in your intestines, moreover, will break down those molecules, and the colour comes from the shape of the molecule, so if you break it down, you lose the colour.
Thank you very much, Jenny. What an interesting question. Let's go to Derek, again in Durbanville. Hi there, Derek.
Hi, good morning. Compliments this season. If a mosquito bites somebody that has AIDS, and then bites you, can you get AIDS?
Hello, Derek. This is something that people were very worried about originally, but we now know that this is not a risk. For one, it's actually quite difficult to transmit HIV via a blood donation in this way. If you've got a needle with blood in it and you take it from someone who's got HIV, assuming that they are not in the acute phase or the final phase of the infection, then the virus load in the bloodstream can be quite low, and if you stick that needle in somebody else, then the actual risk of the transmission is about 0.3%. The vast majority of HIV transmissions in the world occur sexually, but they're still relatively low risk in the grand scheme of things. That doesn't mean that you have to be complacent, though. But when you think about a mosquito, it's much tinier than a transfusion that's coming from, say, a bag of blood or from a needle. Now, the other important point is that the way that viruses that are transmitted by mosquitoes work is that the virus has the ability to infect the mosquito, and the mosquito amplifies the amount of virus in its body, so that when it then goes and bites somebody else and injects its saliva first, which it does to stop the blood clotting when it's feeding, it then is pumping back into the body a very high level of virus particles. Unlike if a mosquito fed from a person with HIV, it would draw into its body a very tiny amount of blood, and there would be a tiny number of virus particles, and then they've got to survive being inside the mosquito and then get back out of the mosquito. So the likelihood of that happening is really, really low, because HIV is not adapted to mosquitoes. It's not adapted to growing in the mosquito, and therefore the virus load in the mosquito and the environment inside the mosquito of the digestive juices all add up to mean that the mosquito is not infectious for HIV. And the same is also almost certainly true for viruses like hepatitis B, but not for important agents like yellow fever, for example.
Thank you very much, Derek. And I suppose the one thing we must be concerned about is malaria, Chris, when it comes to mosquitoes.
Yes, that's right. But malaria is not a virus. Malaria is a very different organism. It's a parasite. It's a very small organism that you can see with a microscope that lives inside your red blood cells. And when the mosquito feeds from a malaria-infected individual, then the malaria goes into the mosquito inside the blood cells that the mosquito feeds on. And the malaria parasite is adapted so that it knows when it's got inside the mosquito, and it then infects the mosquito, travels to the mosquito's salivary gland, where it changes into another kind of malaria parasite, which then increases its numbers enormously in the mosquito, so that when the mosquito goes and bites another person and injects its saliva, very large numbers of the malaria parasites are then pushed into the new person, and that's how it's transmitted.
Let's go from mosquitoes to dung beetles. Hi there. Is it Italo in Melville?
That's correct. Hi. Listening to Simon Gear this morning, he told us about how do the dung beetles go from where they've collected the dung to back to where they were, and they did an experiment in Europe or wherever, and they found out that they actually use the Milky Way. Can this be possible?
Hello, Italo. There's actually a very interesting piece on this in our new Naked Scientist podcast. If you go to nakedscientist.com/podcasts, the programme actually recorded all this last night because the story was published last night. You can listen. Ben Valsler from our team covered this. It's in the journal Current Biology this week, and it is absolutely true. They were making measurements of dung beetles recovering their balls of dung from a big dung heap. They roll them away radially from the heap because they don't want to be near where there are other dung beetles that might, as Ben put it so nicely, steal their balls. So as a result, what they do is, as they're doing this at night time, when it is cooler and obviously it's dark, they have fewer visual cues to rely on. So what the researchers discovered is that they're actually sensitive to the light in the night sky. They're not looking specifically for the Milky Way. They're looking for a light source, which means that they can then roll their ball in a straight line relative to that light source. And the researchers took dung beetles to a planetarium. They actually did this in South Africa, and they did this in a planetarium and were able to put different light sources in different orientations, and this meant that they were able to fool the dung beetles into thinking they were seeing the Milky Way in different orientations, and they used it in order to roll their balls away. And if you hide that light source, they do struggle. So on a cloudy night, then they have a bigger problem than when it's a nice clear night. But this was the first example of an insect being able to navigate using starlight. So it's not just early human mariners that did this, dung beetles do it too.
Okay, so you can indeed go to the Naked Scientists website, www.thenakedscientists.com, to find out more. Okay, Andrew, you've got a question that is frightening me from Lee Glenn in Roodepoort. Good morning.
Hi, Rudy, how are you?
Fine, thank you.
I'm very well. And Chris, how are you?
We're fine, Andrew. Your question?
Good, all right, thanks. Look, Chris, I want to find out, is it true that when you sneeze, every part of the body stops functioning, the heart included?
Hello, Andrew. Thankfully not. And it's also not true that when you keep your eyes open when you sneeze, your eyeballs pop out, because I did an experiment on myself to see if that was true. It definitely isn't. I can assure you it's not.
Christo in Pretoria, hi.
Hello, yes.
Hello, Christo?
Yes, I'm with you.
Yes, your question.
Right. We are now only seeing all the stars which...
Okay, hold on. Is your radio on? Please switch it off and get back to us. Let's go to George in the meantime in Rosebank. Hi.
Hi, Rudy, and hi to the Naked Scientist. I just have a question, and I thought before putting in my application to go and live on Mars in the next 10 years, I should rather find out first. Is there a way or a possibility of people being able to grow food on that planet once they get there in 10 years?
Hi, George. Well, this is the big problem. The only things that we know of that can capture the energy of the sun chemically in a form that we can use are plants. And so we need plants in order to feed us. And if it wasn't for plants, there would be no things on Earth that could live the way that we live today. And so if we're going to survive on Mars, then the energy source that we'll be able to use, we may have things like radioactive sources, but if we want food, we're going to have to grow it. And because there's no way we can take enough food with us. And that means we need to be able to get plants to tolerate conditions on Mars. Now, we're not saying they would have to grow outside. We would have to probably grow them inside in some kind of special greenhouse that's sealed, because the atmosphere on Mars is very thin. It's also extremely cold. So assuming we could solve that problem and get to Mars, is it just a question of planting some seeds, up comes lunch? Probably not, and the reason for this is that Mars has a different day length to the Earth, and bizarre as it may sound, plants, just like humans, have a body clock, and plants can be jet-lagged. And interestingly, if you take plants that are adapted to grow at certain time zones on Earth and you move them so their day length is not what the plant has evolved to tolerate, then the plant doesn't grow very well. And there's actually a gentleman at Cambridge University, I think his name's Dr. Webb, who is Alex Webb. He works in plant sciences at Cambridge University. I think he's working on this, and he actually is looking at how plants can adapt or be adapted to grow with different what are called circadian rhythms or time cycles. Because if we can make plants grow with different time cycles, then we'll be able to grow them both on the way to Mars and also on the surface of Mars. So it's a big problem and it's an important question. But assuming we can solve that one, we'll probably find it relatively easy to build the equivalent of a greenhouse on Mars. That means we can solve the other problems like the soil problem and the water problem and the temperature problem and the gas and atmosphere problem.
Okay, thank you very much, George. Christo and Craig, stay on the line. I'm coming back to you right after this.
The Naked Scientist on Talk Radio 702 and 567 Cape Talk with Rudy Clappy.
Lots of beautiful questions coming through. I've got an email here from Mike, Chris. Mike wants to know, we have an ant problem in general around Cape Town. What puzzles me is that they have taken to drowning themselves in my water glass next to their bed each night. It's not like they're after food there, yet they seem intent on having a wee dip in my drinking water and then they drown, which also begs the question, why do they not simply walk out the way they got in?
I think what's probably happening is that the ants like to explore all kinds of surfaces because they're always looking for new food sources. They may also be looking for a drink. And if the glass has a very vertical side, which it probably does, or even a curved side like a concave surface, the ant is going to find it harder to stick on because the ants are using tiny claws on their feet in order to wedge into tiny imperfections on surfaces so they can get a grip. And if they sort of slide down the side of the glass, they then can't get back out again. So it's just in an ant's nature to go exploring, and I suspect that the water just happens to trap them there. If you were to set up a trap somewhere else, you'd catch equivalent numbers because they're just going everywhere. They do this in our house here as well. It's not just Cape Town, I'm afraid.
Christo in Pretoria.
Hello there.
Yes.
My question to the naked scientist is the implosions that happened billions of millions years ago of the stars, and we are seeing the light now coming or disappearing. Now, what happens to the sound? Because I stay in Pretoria, not far from Maintjieskop, where the cannons are shot. And, you know, you hear you see the smoke, and later on you hear the bang. Is that bang from those implosions eventually going to get to Earth? The noise.
Hello, Christo.
Yes.
Lovely question. You're referring to stars that end their lives in this giant cataclysmic explosion called a supernova. And when this happens, a star blows itself to pieces and it emits a very bright flash of light. That's the supernova. This includes gamma rays and X-ray flashes which travel through space, and we eventually see them here, sometimes billions of years after the star has died and disappeared, and were you to go to where that star was, you would see it was no longer there. But light is a very different beast than sound, because light consists of tiny particles of energy which we call photons. Effectively, it's a wave. But sound is still a wave, but it needs a medium to transmit through. Sound is a compression wave, and it's where atoms or molecules in a gas cannon into each other or in a solid, and they transmit vibrations which are then transmitted into your ears, and in the ears they make your eardrum vibrate. Now, a star in space is by definition in space, and space is a vacuum. And because there is no gas there, you would not be able to hear the shockwave because there is nothing to convey the explosion and the vibrations from that explosion to you. You'd certainly see the radiation, and you'd certainly feel the radiation if you were close to it, but you wouldn't be able to hear it. So were you to accidentally exit your spacecraft in space and scream your head off for help, no one, unfortunately, would be able to hear you.
All right, and thank you very much, Christo, for that question. And we have Luke. Luke in Hout Bay. Hi.
Hi there. If the Earth is spinning at 1,600 kilometers an hour or so at the equator, how is it that we're not able to feel that speed? And, you know, how is it that we just remain standing up and it doesn't affect us? My question.
Yes, hello, Luke. You'd think to yourself, if you were to stand on the outside of an aeroplane that was flying along at just a few hundred miles an hour, or 500 kilometres an hour, then you would certainly notice the air rushing past you and you'd feel a force on you, and you'd think, well, if the same is happening on the surface of the Earth, why are we not being whistled away? And the answer is that yes, the Earth is turning, and yes, it's certainly turning at 1,600 kilometres an hour or so at the equator, because the Earth's circumference means that it takes at that speed about 24 hours to go all the way around. So why don't we notice it? And the reason is that in the same way that when you dip your hand into the bath and swirl it in a circle, slowly the water starts to move in the bath with your hand and you've got a whirlpool. Well, the atmosphere is doing exactly the same thing. And as the Earth spins round, the air that's in the atmosphere turns round with it. And the result is that everything is moving together, and consequently you're not moving relative to the air. So apart from noticing the local breezes, which are slight differences in the velocity of the air, because the air velocity is the same as your surface ground velocity, you don't notice that you're spinning at that speed.
Anton in Belleville, hi.
Hi.
Yes, Anton?
Hello, Reece. Chris, just a quick question. I heard, I think on the radio long ago, that if I burn myself, I should put my finger in flour or put flour on, and we tried it, both my wife and I, several times. I burned myself badly the other day, 4 fingers under a pot. Stuck it in flour, just normal, ordinary white flour, for a long time, probably an hour or so. But everything went away. I had no marks, no blisters, no nothing. How does that work?
Ooh.
Anton, you've got me fooled and baffled. I have no idea.
So you must go burn yourself now, Chris, and experiment.
I wouldn't advise repeating the experiment. Laudable as it would be in the name of science and medicine, I wouldn't advise you to try again. I don't know why that would work. I can only think that the flour might protect the skin a little bit and cushion the area. The thing with a burn is that what you've effectively done is to subject tissue to thermal injury. When you apply a hot object to your skin, the temperature that the skin is exposed to is beyond the point at which cells can survive. This is largely because high temperatures denature or break apart the enzymes and proteins that make up cells, and they also make other chemical reactions go too quickly, which effectively lethally damages the cells. The cells die, and they leach out all of the contents that are in them, and this is very inflammatory, so the immune system gets excited and moves in to clean up the mess, producing inflammatory chemicals in the process, and this then causes the sustained pain that you get because it winds up your nervous system, basically drawing your attention to the damaged area so that you pay attention to it and protect it and make it better. But you've got to replace the cells that have been damaged, and you've got to remove all of the debris that's been caused by the death of the cells and then fix up the tissue. So a burn is a healing process. So I'm not clear why the flour would be able to make this happen any better or any more quickly. It shouldn't, because flour is just starch. I wonder if perhaps by rushing to get the flour on quickly, you removed your hand away from the source of heat. Maybe you washed it in the process before you put it into the flour bag. I don't know. But I wouldn't advise you to repeat the experiment, but if it worked for you, hey, flour's usually relatively sterile. You'll probably be all right.
Okay, Anton, stay away from the pots and the stove, please. Chris, we'll chat to you again next week.
Thanks, Reedy. Have a great weekend, everyone.
Cheers. And our conversation with the Naked Scientist will be available as a podcast. And you can also visit their website on www.thenakedscientists.com, and you can download those podcasts that Chris was talking about, or follow him on Twitter at Naked Scientists, plural. Okay, one word, plural, at Naked Scientists. Back in a moment.